Plum is broken. I mean, there are memory leaks, but also you can't have enums with more than 256 variants. And that's what I want to fix today. So I've created an enum here that's quite big, that has 257 variants. And I haven't run this code yet, so I don't know what's going to happen. But I think if we use that enum, something's going to go wrong. So let's do that. Let's say, let's create a function that takes an int and it returns the value of that big enum. Maybe it even returns the last one, so 257. All right, and then in here maybe we just call foo and then we debug format that. I think is debug format in scope. Yeah. All right. Yeah, let's try to run that and see what happens. I have no idea. Okay, so it's function returns something different than its claimed return type. Oh right, yeah, that makes sense. Yeah, this is supposed to return a task. Now let's print that, I guess. Like this, print this, and then let's exit. It's kind of worrying that the type checking takes so long, but meh. Okay, that's interesting. Okay, so something is happening here. Out of jump table bounds. I don't even know what that does or what that's doing. Out of jump table bounds. Basically, we have some jump table instruction which takes the number of items in the jump table, which is a byte, and then it pops a byte from the stack and prints that. That's maybe, I kind of know what's happening, I think. Probably the number of entries in the jump table is calculated to be 257, but storing that as a byte in the bytecode actually just stores the lower byte of that number. So this would probably just store a 1 and then like a 0 or 1 or something like that, and yeah, the byte is bigger than that. Well, that makes sense. So where in the compiler do we need to fix stuff? We have several compiler stages. Let's just go through that. Parsing something that works. Yeah, then type checking that should work as well. Monomorphizing functions for concrete types, sure. Adding dupe and drop instructions, sure. Deciding on not memory layouts, but where to put pointer indirections and stuff like that. That works. But then in here, the pesto to waffle. That's where things go wrong. And actually, I think in the waffle to ground, we can also add some sanity checks. So let's do that first, I guess. A waffle to ground. That's in here, and that's in here. So when we are compiling an expression, do we have a switch or something? Oh yeah, here's a switch. The switch has a byte. and then we go over the switch cases. I see. I guess let's print the waffle and just look at that and see where that needs to be fixed. So yeah, let's just enable that, printing the waffle, and I think that's it. I mean, yeah, we cannot, yeah, actually let's print the optimized waffle just for, because that's going to be a bit more concise. Oh man, those compile times. All right. That's something. All right, what's going on here? We have lots of code. Dang. A lot of code. As in the debug formatting, these are stringifications of all the values. That makes sense. That takes up a lot of space. It doesn't even fit on a single terminal screen. Let's pipe that into a file, I guess. Well, that's say ground. Let's remove that and then run that again. Yeah, I hope that's printed on standard out and not standard error. Well, never mind. Yeah, let's do it like that, I guess. All right. Here we go. So we have an array iterate function, which, I mean, sure, you have some dupe function and drop function of dynamic, of bytes and iterators and whatnot. Digit. That's quite long, but makes sense. What's the main function? Let's look at that. Main function. Alright, so here we have a byte 208 for some reason. Oh, I see. Because that's the index in there. Like the enum variants that are sorted alphabetically, and this is apparently the index of the variant that we want. Yeah, alright. So what can we improve? I think we want to choose better memory layouts. The enum cannot just currently enums, the memory layout of enums looks like this. Layouting structs, layouting enums, yeah. The memory layout looks like this. We have basically the payload, and then a tag that tells us which enum variant is active. And for example, if you have an enum like this with like 3 variants, we look at the payloads, we memory layout those. This has as a payload basically an empty struct, nothing, which has a size of 0. This one is an int, which is 8 bytes. This one is a byte, which is a single byte. And then we'll just take the biggest payload. So the payload in that case would be 8 bytes. And then after that we put a single byte that tells us which of these enum variants is active. That means when we switch on an enum, we then we just look at the last byte, and that tells us which variant is active, and it also tells us how to interpret the payload that is in front of that. And here we'll probably need, for these variant things, we'll need the tag to be not just a byte, but an int. And that instead have like a tag size in here. Because not all enums just want to store a single byte. There are ones that want to store 2 bytes, or maybe 3 bytes, although that's kind of going crazy. Yeah. I think that makes sense. Yeah. What else? So we have the tag has an offset and a size, and then there's a mapping tag to variant, which is just going to be a map from ints to strings. And the individual variants, they have a tag here as well. All right. Yeah, and let's just use the int in here, and instead of the lower byte, which kind of wraps around and is kind of cursed, let's instead just have ints. Cool. And then we need to calculate the size of the tag. Yeah, the tag size. So what's the tag size? I think we need to, let's choose that up here. I think there are enums with a tag size of 0. For example, if an enum only has a single variant, there's no need to store a tag even. Because, of course, it's going to be the single tag of the enum, the single variant. So let's start with a tag size of 0, and then kind of check if it's like 2 to the power of tag size, if that is enough to store the, if that is not enough to store the number of enum variants, like that, then we need to increment the tag size. Then tag size plus equals 1, and we do that in a loop, otherwise we break. How is that? Fine. If this is larger or equal to the variance size, then we break. Let's do it like that. Which means if we have one variant, for example, 2 to the power of 0 is 1, which is larger or equal to 1. So then we break immediately and we have a tag size of 0. If we have 2 variants, then we'll actually need to store a tag. So there we would say, this 2 to the power of 0 is 1. That's not larger or equal to 2. So we increment the tag size. All right. And then add like 257 enum variants. That's 256 is not larger or equal than 257. So we increment it yet again, giving us a tag size of 2. Yeah, that makes sense. All right. And that means we have a tag size here. Pretty cool. What else do we have? We have memory layout enum. Oh, this does not work. Oh, there's this one, this operator, this star operator. Is this? Yeah, this is the power. Yeah. So it's actually like that. I like that. All right, and then this is everything we need to know about enums. Yeah, this is just structs, and up here memory layouting arbitrary types. Well, we memory layout the enum, and then we create a memory layout where the memory layout enum that has a size. That's interesting. Let's see, size, indeed. Oh yeah, this is the max payload size plus the tag size. Sounds reasonable, I think. And then in here we can, when you create an enum, if that's a tag, we actually need to kind of break that up into multiple bytes. So let's have a list of, let's part stop push. Yeah, let's do that multiple times. So let's kind of put that inside the switch. Yeah, here we just push some padding, and here we push things multiple times. So basically for every size, for every I guess, in the range from 0 to layout.tag size, we want to push the individual byte of the tag. Are these stored in little or big endian? I think in little endian. So if you have 257 variants, for most of the variants, the first byte of the tag will be the actual useful, the tag like this, like 0, 1, 2, 3, etc. And then the actual last byte of the data structure of the enum will be 0 for all cases except 1, where it's 1. Yeah. So we memory layout the enum, and then we get the variants, or the layout of that variant. Yeah, that doesn't contain enough information to do stuff. Yeah, so let's not do that. Let's store this as enum layout and this as variant layout, and then we do enum layout.variants, and this will be the variant layout, and here we get the enum layout tag size, and we just push the actual tag that we want, but only the modulo 256. And that's going to be a waffle byte. Yeah. Of that converted to a byte, so the lower byte of that. Oh, hang on, lower byte, we can just do that directly. I think that's fair. And then we'll also, do like tag equals tag divided by 256. All right. So for the individual variant parts. If there's a value, I mean, first there's a value, you know, with the actual value that we push to this list. Then we have padding in there, and then we have a waffle byte. Possibly a tag, possibly consisting of multiple bytes. Yeah, I like that. That makes sense. And then we turn that into an aggregate. Fair enough. Let's compile it. That won't work. Yeah, maybe constructing the enums might work, but switching on that won't. So expected closing parenthesis of the call. All right. What? The push. Oh yeah, there's one additional closing parenthesis in here. Actually, can we maybe remove the debug printing? Hang on, the debug formatting, and just do, you know, calling foo and then doing nothing with that result. Does that get like garbage collected or something? Oh yeah, tag size plus equal, that's not a thing. And the memory layouting, that's just tag size equals tag size plus 1. Alright. Yeah. So we have a switch. How do we do that? We take the condition, we memory layout that. All right. And then for every layout, all right, we put something into the mapping here, which I guess, and then this is a slice of the size of the variance. Actually, I think switches need to be compiled into possibly multiple switches, you know, because if you like the switch switches on a byte, but a byte is not enough for our use case. If we have an enum that uses 2 bytes to represent a tag, we actually want to switch on, I guess, the last byte first. Then that tells us which is it, one of the first 256 variants or one of the later ones. And then we can use that to then switch on the actual, kind of within those variants, switch on something. I'm not entirely sure how I want to model that. I just know that we can't just naively do that. We have a waffle switch. Yeah. And then cases is uninitialized slice. For all the elements that we have. I don't exactly know what to do. Like I know what I want to do, but how to do that. I mean, okay, that's, you know, kind of, this is still valid. I think we still want to memory layout the parameters, put mappings in here, build up cases even. But then in here, we don't just want to put them in a switch naively. Instead, we might use multiple switches down here. All right, so kind of we have to, you know, basically if cases.len is larger than 1, then we want to do some stuff and kind of group these into bunches of 256 variant cases. Or rather, like for layout is the memory layouted enum. Alright, so for every byte, for every I in the layout tag size, we want to get the corresponding byte from the enum condition. So the tag offset, we want to get a single byte from tag offset plus I believe, plus layout dot tag size minus I minus 1, possibly. Oh. Yeah, this will first switch on the totally last byte of the enum, and then on the byte before that, and then the byte before that, etc. Before I do that though, let's look at the waffle and then decide what to do. Hoping that it doesn't just immediately optimize out the thing. Oh, it does. Yeah. All right. Fair enough. Oh, this is interesting. Well, on the main function, turns exit. Actually, you know what? Let's make it so that this returns a big enum. Foo of A. And then we should immediately see the kind of memoried out that the enum has in memory. Yeah. Oh, that's horrible. All right. What's going on here? We have first of all a byte, and then 8 other bytes after that, for some reason. Why is that happening? Oh, hang on, let's print the waffle. No. Oh, we do that, right? Oh yeah, we do. Why are those bytes there? Pesto to waffles. So we have an enum. Alright. Okay, apparently the tag size is 9 or something. For some reason. That's strange. Yeah, okay. Not what I want. So why is that going wrong? We have check. The tag size is initially 0. And then we loop if 2 to the power of tag size is larger than the variance, than the number of variants, then we break. Otherwise we increment it. Alright. Let's maybe add a logging here. We need a tag size to store this many variants. I think that's a reasonable debug message. I see. Because every byte of the tag size is not just providing us with 2 variants. No, it's providing us with like 256. Because this is an entire byte. That makes sense. Alright, yeah. This is not in bits but in bytes, so I see. Yeah. And then 9 also makes sense. Yeah, 1 more bit than 8 bytes. Alright, so the tag size is 2. We need 2 bytes to store this giant enum of 257 variants. And it's represented like this, which is quite okay. Yeah, it's nice, I think. Actually, let's construct the latest, the last variant, alphabetically sorted, which will just concac by calling it Z, and just returning that over here, rerunning that, and let's see. Yeah, okay, that seems reasonable. So we have 258 variants. The first 256 are fine with just using this byte, and the second byte will be 0. And then the variant number 257 is, this byte is 1, and this byte is 0. And then 258, the last one, this is 1, and this is 1 as well. Alright, then switching on that enum. That's kind of the next step, switching on big enums. I could just copy this and turn that into a switch, I guess. Let's do that. Yeah, let's create that enum and then switch on that. Dang, that's many variants. Well, oh, okay. Okay, and every case just returns 2 for some reason. Why not? And then that's an int that we return from the main function. Let's do that. All right. Oh well, that's the constant folded. I guess. Because this foo function is inlined, and then we switch on the enum that is known at compile time. So let's not do that. Let's instead say that, and where's the foo function? And here. Now let's say, if a is 0, then we return z, otherwise z. I mean, that's, I think the compiler doesn't optimize that. It doesn't compare multiple switch branches and check if they are actually equivalent, and that makes the int, the switch obsolete. All right, so we have several enums apparently. Let's see if these are useful. Okay, so we need a text size of 1 to store 3 variants, correct. Of 1 to store 2, yeah. Same. Okay, that makes sense. And then this one is interesting. So here we need a text size of 0 to store 1 variance. You might wonder, why do we have a text size, why do we have enums with only 1 variant? That doesn't make any sense. But actually, when you create an enum literal like this, the type of this will just be, enum like ZZZ. This is the type. And then only when you have a switch where the branches evaluate to different enum variants, or you have a function that kind of claims a return type that's more general than the actual code inside the function, then these kind of very special cased types with only one variant, they get cast into the more general types. So it makes sense that there are enums with only 1 variant that don't need to store anything in here. All right, so then we want to switch on that. And it says waffle member offset to big 0. Offset to big 0. In waffle member, that's weird. Let's check that out. Waffle member offset to big. Let's just print a better error message there. I'm not sure if that fails for the enum with 258 variants, or if that fails for the enum with only 1 variant, so the tag has offset 0. Yeah, okay. So we try to access 1 byte of something that actually stores nothing at all. So let's go to the switch down here. We have these cases for the individual variants. think what we need to do is I'm just wondering, like, if we only have a single case in here. We don't actually want to emit a switch. We just want to execute the case code basically directly. So that would be if cases dot len equals 1, we get the case and we, what's that? It's a waffle body. Let's check that out. So a waffle body has locals and it has a return ID. All right, I think we want to add that. Kind of want to add those locals to our builder, our body. Yeah, our builder. So basically for every builder dot push, something like that, maybe, and local, like the case body or something is cases.0, and then for all the locals in the case body locals, we want to this has a list of locals, so we want builder.locals pushing the local. And then we want to return whatever the last expression of that is. So how do we do that? We just return case body that returns, right? It's going to be a waffle expression instead of emitting this switch. And the switch, we kind of only emit that as long as we have more than one cases. Yeah. Stuff like that. You know? We have this list of cases, which may be like millions of, not millions, hopefully, but lots of cases. And we group groups of 256 cases into a single case, getting a list of cases that is way smaller, and kind of emitting a switch that decides which of these cases we want. That makes sense. Ooh, okay, so let's organize my thoughts here. And groups of 256 cases into a single case. Yeah, I'm building up new cases. Yeah, I don't know exactly how many, we'll figure that out. That will be a list of waffle bodies. Yeah. And then what we'll do is we will we kind of want to create a waffle body, which needs a waffle body builder, which we can create on a DAG. So we can do builder.dag. Creating a new body builder like that. Inner, I don't know. And that body builder then, I think bodies in the waffle, they don't have parameters anymore. Nope. They just have local variables, which this one doesn't actually need, and it has a return value. And then we can do .finish, giving, passing in a return expression, a waffle expression. Okay, so we can just do that immediately. Yeah, let's also have like a counting variable in here because, of course. I equals I plus 1, all right. Yeah, basically we want to switch on the tag offset plus tag half, maybe. And we start at the tag size -1, which will be the last byte of offset and tag, maybe. We start with the last byte of the tag, looking at that. Oh, hang on, actually. No, actually we start at 0, I think. Yeah, the tag offset plus the offset in the tag. And then in here we will have the kind of the sub range of those cases that are relevant to that tag. So basically for relevant cases is perfect. The existing cases, yeah, the subslice from I times 256 to, well, I plus 1 times 256. Kind of the maximum between that and the minimum between that and the number of cases that we have. And the number of cases would be cases.len. Whew. That is some deep code. And then in here we have relevant cases. No, we don't break right now, which is unfortunate. So we know how often we want to do this. Yeah, you know what, let's leave it like this for now. And then we can fix that later. So if this I plus 1 times 256 is larger than something, larger than the number of cases, then we break. And then here we say cases is new cases, something like that. I'm sure there's like an off by 1 or something in here, but we'll figure that out. All right. So what's going on here? This probably fails right here. This waffle member of the tag offset, which is at. Oh, hang on. No. Oh. We need a tags as well. All right. So I think we're switching on something on an enum with only 1 byte. And yeah, so the size of the enum is 1, and we switch on the first one, so the tag offset is 0, offset and tag is 0, and we have like 2 cases or something. So let's debug, print that. And then we build up new cases by taking a subslice of the first 0 to 2 cases of all the cases, basically, saying hey, we want to switch on those based on the tag offset plus 0. All right, relevant cases, nice. And then, oh, hang on, new cases is, we don't actually push something to that. Yeah, we do need to push that. So new cases dot push that. All right. Oh, I see. And then we don't run into this cases len equals 1 thing, and that's why stuff goes weird. Okay, that's fine. All right. Let's see. Oh, this is quite promising actually. Oh wow. Okay, let's see. We first of all have the main function, and it calls the foo function with our parameter. The foo function, in the one case it returns an aggregate, and in the other case another aggregate. Those don't need any sort of those don't need any data. These are empty aggregates because both return the same type. So the type of this of the main function of the foo function, of the type of this expression here is this, an enum with only one variant, which means that it doesn't even need to store a tag, a single tag. It's just the size of that is 0. It's an empty aggregate because there's only one possible value that this can have. And then when we want to return that, then we actually kind of need to cast that to a big enum. Oh yeah, which is a big enum, so it needs 2 bytes for the tag. And because this is the last one, actually let's maybe add a couple more. Let's say ABC, AAA, and then 1 byte will be like 3 and the other one would be 1, I believe. Oh yeah, true. So when we switch on that enum, over here, we need to handle those cases. What was it? AAA and ABC. Yeah. Alright, so this returns an enum. The enum is so big that it needs 2 bytes to store the tag. 1 byte is like these are little endian encoded, the little endian encoded index of the tag 3. And then in the main function, we look at the last, the second of those 2 bytes. And we check if that byte is 0, then we actually want to switch on the first byte of that same enum. And that kind of tells us we're basically looking at the cases 0 to 256. 0 to 255 inclusive, those are 256 variants. Otherwise, if the last byte of the enum is 1, then we know that it's one of the other cases here. Oh, that's pretty cool. That is actually pretty amazing. Okay, yeah, so this looks like reasonable code. It doesn't work yet in the ground VM because the main function is supposed to return a task, which has a size of 49 instead of just an int. But we can fix that. We can say, let's actually factor this out, I guess, into a function. It's a function numberize some big enum value. Return as an int, and this function just switches on that value. And then the main function, we can create a foo, we can numberize that, giving us an int, and then I don't know, we can format that, I guess, and print that. And then we will exit. So that's a valid task. All right, I hope this is just memory leakage. Yes. Oh yeah, we print 2 and then we exit. That's pretty cool. Actually, let's see, we create z. Let's make sure that this is the correct one by returning, I don't know, 90 in that case. All right, big enums work. That's pretty cool. And then, just for fun, let's create an enum with only a single variant, and let's see how that looks like. And let's say big enum is an enum with only 1 variant. Here we switch on that 1. I guess, yeah, this needs to return that. And I'm especially curious about the underlying code here that we generate. Oh damn, that's actually a lot of code. I think for like formatting numbers and stuff, we pull in a lot of stuff. Alright, yeah, we have some lambda, we have some dupe, we have stuff. This is the interesting part. Calling the foo function. Okay, yeah. Oh yeah, of size 0, you see. Because this enum only has a single variant, that doesn't even store. Like that doesn't even take up memory. And then we format a2. Okay, yeah, fair enough. That's the simple one. Okay, so this foo function. Oh, I see. It was like completely constant folded, I believe. Yeah, because we no longer have a switch in here that switches on this sort of type. Which makes sense. Yeah, I like that. Okay, yeah, let's remove some of the debug printing and then commit that. And then that's it for this video. So, in here, oh, I could clean up that code. I should do that. So here we have the cases, and then this code is kind of nasty. This code at the bottom, that's fine. But in here we have kind of loops and like variables and things that are difficult. I think we don't even need to check this. Like we don't need to check the length of those cases. We can just say, yeah, basically for every I, even though I is not even used here. Like unused. In the tag size, they output tag size for every byte. And we want to reduce those cases. And then afterwards we can assert that, you know, if cases dot length is not 1, then make meh. I'll redo. Yeah, these should have been reduced to a single case now. And then, oh yeah, this is like 0 to, yeah, tag size, sure. And then we do this. Oh, hang on, offset in tag is like, it's 0 in the beginning, and then in the end we increment that. We can just use this one right here. Boom, like that. That is clean. Can we do something similar for this inner loop? Because I think we kind of know the, like we can calculate the number of iterations that this loop needs, which is the number of cases, not divided by 256, because it's, I kind of want to, oh, I think it's like rounded up, and but otherwise divided, yeah. Even though like the last unfinished case, you know, where we don't have 256 variants, that still becomes a case. So a rounded up division, kind of. And I think the way to do that is by doing like in 0 to cases.len plus cases.len minus plus 255 divided by 256. That, like that's a rounded up division basically. And then we no longer need this or this break condition. We can just use the I in here. new cases. As a list, and then we push stuff there and convert that to a slice. We can, we already know the size up front, so we can create an uninitialized slice here. By calculating that, actually. New cases, perhaps. And then we create a slice for those new cases. And then for every I, we don't push that, we just set that. So we do new cases.set that I to something. Like so. Amazing. And then relevant cases, I think we'll actually inline that in here. Clean. Yeah, this is no longer needed. This is, yeah, we'll keep that. All right. Yeah, I like that. Let's see if that still works. That's kind of important. Maybe I should also test that for the big enum. Yeah, that's just leaking memory. That's fine. Well, not fine, but expected. I should fix that at some point. First, though, yeah, these were the changes to test that for the bigger enum. That should print 20, and it does print 20. All right, yeah. Yeah, let's disable the printing here. Yeah, I'm actually fine with not using ePrintLine, but using printline. I think I want to do that everywhere, because if I enable that like explicitly, I think that's supposed to be part of the output and like easily pipeable into files and stuff like that. Cool. Let's commit that. So in here, print more stuff to standard out instead of standard error. Yeah, that's not gonna commit that. Oh yeah, this is fixing some bugs. Fixed. I did that previously, I think, at some point. Sure. Here we do, oh yeah, supporting enums with more than support big enums. Boom. Amazing. All right, and that's it for this session. Yeah, big enums work. Really small enums with only one variant don't even, they take up 0 bytes. That's pretty cool. And I guess the next step would be, well, I don't know. We'll see. Maybe fixing memory layouts. That would be nice. Yeah, so see you then.